talk. And so what I'm going to do, well, if I end up talking in an hour, we'll have to cut, but that's okay. Interrupt and derail me if you'd like. So first, I'll do a lightning review of fusion categories. I figured not everyone here really knows this. Certainly some of you know it very well. Some of you may not. And then in particular, I'll use these fusion categories to make lattice models, including some very well-known ones, Ising model, for example. But what setting them up in terms of fusion categories does is allow you to do topological defects. And insofar as my role in the story is, this is a couple papers I wrote with Dave Asen and Roger Mung in 2016, 2020. So those papers have been noticed, I guess, enough to be borrowed from extensively. But then I wrote a paper by myself for almost the same time as the latter of the papers with Dave and Roger came out, talking about conserved currents. This one doesn't seem to have been noticed so much. So I'll try and at least get to about that. But if you derail me to ask questions about this, that's okay too. I can at least summarize very quickly. And in particular, one motivation, this is kind of these, so point is, in these lattice models, there's an interesting construction of conserved currents. That's what I'll tell you about. And they have something interesting to do with integrability. That won't take long to tell you what's going on there. So anyway, so I drew this picture here. And so fusion categories are this huge thing, lots of interesting things to say about them. But I'm going to be a very physicist type thing here. I'm just going to say this is what we need from them. And can...
We have to leave at 11. We book this room again in the afternoon.
Oh, okay, we have a part 2. They can't move their seminar back. I mean, that's pretty rude of them. Okay, so I'll finish up. Right, so anyway, so probably I'll get to these through in the hour and maybe say a little bit. Okay, so here's the part. So again, I want to do fusion categories as basically a tool to do interesting physics with. And so let me tell you the rules of this. So as I indicated, where's the eraser? Anyone see an eraser? Right, so I said, just repeat. So you take this thing I like to call fusion diagram. So what it is a labeled trivalent planar graph. Let's not worry about complications if you put it on the surface. And it turns it into a number. And there are rules to do this because, there's lots of planar fusion diagrams, these labeled planar graphs. And so you need consistency conditions. So there's a bunch of rules that allow you to do this. So the basic one is what's called an F move. So I'm going to write it out just once in all its glory and then omit details, but just so you see it once. Okay, so this is a subgraph of your big graph. And what it says, so let me just use my conventions here. So these are the 5 edges. And I'm using an old convention. Okay, so these are called F symbols, so just think these are numbers. Now, I've simplified things greatly. Categories in general are much more complicated. You can put arrows on them. You can have things going on the vertices, but I'm taking all the simplest possible things so that all I need is to draw a vertex, and I need that. And so what the category tells you is that in this map, from this diagram, to the numbers, from this labeled graph to the numbers, it's invariant under doing this manipulation. This is the basic one, but let me now tell you a little bit more about this algebraic structure so that it doesn't seem so bizarre. So the first thing you do to define the category is a fusion algebra. And this is of certain objects, which we just label A, B, C. So these will be the labels on the edges. And the fusion algebra then just tells you when you fuse two things together. So you can think of, for example, tensoring different representations of Lie algebras. Here, you can't quite use a Lie algebra for technical reasons, but you can use a quantum group algebra. And so these are non-negative integers. Yeah. That's about to say, right. So that's right. So these are in general non-negative integers, but since I'm not labeling the vertices, in my case, n is 0. And I'm not worrying about upper and lower and all these many complications. And yeah, so you could label the vertices if you want there. And so that the point is, we then have a vertex if A, B, C is allowed. Okay. So we also, okay, so that's this fusion algebra. So that tells you the graphs that you're allowed to have. Okay, and then, so the F, before I put that up, the F is basically, so again, I'm using this is data. So these are numbers. So the point is the mathematicians can classify fusion categories. So there's consistency conditions for this map. And so you get things like the pentagon equation. I'll draw a thing called the hexagon equation later on in the talk. So all these consistency conditions. So, but happily there's solutions of these consistency equations. And you can find these numbers for a given choice of this. So just to keep something in mind that we use. So one of the fusion algebras, which we call Ising, has three objects, which we call 1, sigma, and psi. And well, so 1 is the identity. And then the other non-trivial one. So that means anything times 1, A tensor 1, it's A, and then sigma times psi. So that's an example of this, and then you can construct all this stuff. So that's the most detail I'm ever going to need. Let me write down two things that follow when you have these consistency conditions. You find two useful relations here. So if you have a bubble in your picture, so you got a line coming in, A, B. And so what the D's are, so these are special F symbols. So D is some particular F with some things going on there, which I won't bother to write out. But what D is, and these are called the quantum dimensions. And the reason D is called the quantum dimension is, well, if you look at this, well, okay, so A has to be equal to B. But now let's set A equals B equals the identity. So what's the 1 there? Then you can just omit the line. And then all we have is this picture. And for the identity is 1. So then this picture just gives you E. Okay, and so this, if for people who know anion theories, you can think of it as sort of the number of degrees of freedom running around the thing. If you were doing Lie algebras, D would be just the dimension of the representation. but we're doing something more complicated, quantum groups and things like that. So the D need not be an integer in this case.
B with a line on it. It's a line, it's a graph.
Oh, yeah. Sorry. Good. No, good for it. Thanks for asking, Dave. Yes, the point is what all these rules let you do is just change around the graph without changing that thing at the end, the number that comes out. Which, I'll say now, the word people use in this track is the evaluation of the graph. So it's turning the graph. So these manipulations give you the same evaluation at the end. So it's a way of relating graphs. And so by doing these things over and over, you can reduce that thing up there to just a loop. And then that's just this number D, the quantum dimensions. Oh yeah, so I didn't write it down because I forgot. I forgot to write it down at F. But the point is, when you run through all these manipulations, see, the only way to make this consistently is if this is true, and then you find D's are particular values of F, but with some particular choices. And so we just named those D because that's nice, but it's just a particular F symbol. Sorry, I forgot to write it out. I mean, there's some identities in here.
But it's probably only in a particular gauge.
Yeah, of course. I mean, this is true in any gauge. Obviously, in these things, there's sometimes gauge choices. I'll pick a gauge. Yeah. I mean, this relation is always true. Yeah, I mean, there's probably some stupid phases you can put in there, but the conventions, you choose D, so it's in a unitary category, D is always a positive real number. You can always find a gauge, which is that, so always, yes. Yeah.
But then it's not evaluated, it's not evaluating R, not in C.
No, because the F symbols are not always real. So the point is to read. Yeah. But to get there, I have to take, so I should say it's a linear combination of all these graphs. So what I can keep doing, but then the coefficients are the F's. So good question. So the point again, this in the same sense as I said before, you can take a graph with this and I have to replace it with the sum over graphs. And these things aren't real. And for those of you who know, or have heard of knot theory, this is exactly what you do to evaluate the Jones polynomial, to find the Jones polynomial. And so the point is you pick a particular category and that gives you a particular map. I mean, different categories will give you different numbers, just like there's a Jones polynomial, but then there's lots of generalizations, Alexander polynomials and things like that. Okay, and the last relation I want to know, just to give you the idea, the point is you can do something that looks bizarre. Why would you ever do this? I take two lines that aren't together, but then I can write them as a sum over lines so that seems strange, but it turns out to be useful to do that. One of the reasons it's useful when you're manipulating these things, for example, from this one, you see, for example, if I ever have anything like this, it equals 0 for A not equal 0, A not equal to identity. So you use these things, and so that's the kind of thing it's useful. Yeah. And good question, by the rules of fusion category, yes, because there's only a finite number of objects. There's an interesting question for physicists. I mean, we can invent things that don't have a finite number of objects. It doesn't satisfy the rules, doesn't satisfy the theorems that mathematicians prove. But on the other hand, maybe it all goes through. I think there's probably people in the audience who could say more about that than me. But the point is, well, for technical reasons, yeah, we'll see, because that's the way the mathematicians like to do it. So that's why you can't use just representations of an ordinary Lie algebra, because for SL2, there's an infinite number of representations. But for quantum group algebra, there's a finite. Simple representations. That's right. Yeah, sorry. Simple representations, absolutely. Sorry. Good. All right, so that's actually it for fusion categories. Now I want to start to get to the physics. Sorry? Yeah, I could do that, and then yeah. I mean, I can do all these and these consistency conditions like the Pentagon equation to make sure. Yeah, so I could then do this. Right, if I did that, I would be saying it's sum over some diagram, some d times that, and then so all that's so you can do anything you want. This one that would make it more complicated. Might want to do that. So I'll leave those up for a while just to remind you. Kinds of rules. So there's obviously lots more you can do. Those are a couple simple ones that are good too. So okay, good. That was my lightning review. It's too lightning. Then part 2, I'm going to talk about a certain class of lattice models. Pull these rules, and again, to reiterate something I said in the introduction, the point is if you define lattice models in a certain way that I'm about to describe, then the topological defects in this model come for free. Which is a remarkable thing. So there is a free lunch sometimes. And so this is what I'll talk about. So this is part 2 of the talks of lattice models. Okay, so now we need to define, you can do this for classical lattice models, but for simplicity, I'm just going to do the Hamiltonian version. So the first thing we need to do is define the Hilbert space. And to do that, specify one object in the category. And I'll give the example for icing in a second. So we'll just call that row. Okay, to define, and it shouldn't be the identity because you'll see in a second that would make it trivial. Okay, and then I draw a picture in the same sense there. All right, so I draw this picture here, this line here, but then with these things, and this is now this picture. And the point is the elements of the Hilbert space, I should say basis of the Hilbert space, is formed of all allowed diagrams. So if I label this thing H1, H2, H3, 4, dot down the line, that means in this thing n row Hj, Hj plus 1, well, that's 1 in my conventions. Dots there if you want to allow. So these are the elements of my Hilbert space. That's all. Anything that's a basis for, and we're going to have some quantum Hamiltonian. Yeah, well, so I'd say L, so in a size L system, I would have L vertical lines. Yeah, it's a fixed sum, a fixed number. I mean, you can pick it whatever you want. Today, I'm going to completely avoid worrying about boundary conditions. But in this setup, just have to be careful with what you do at the ends. So this is going to be a one-dimensional model. I'm specifying the full Hilbert space. Yeah, so what's interesting now is you have to know the whole Hilbert space. Now I'll give you the icing example in a second where it sounds like it's much simpler, and you'll see why. But that's right. I'm giving a rule for anything where it's a local rule that determines it. But of course, what's here determines what's allowed there, and so on. Right, because I have to satisfy this. So let me give an example. So for the icing category, remember the key rule is we have sigma times sigma equals 1 plus psi, and sigma times psi equals sigma. Okay, so say I take rho equals sigma. All right, so let's say I start here. So this is rho, but that would be sigma. So now let's look at, this is going to give me the Hilbert space of the icing model in a bizarre way, but there's a payoff for doing this. Okay, so say I start with sigma. There, we can do the other way, but I'll pick that boundary condition. Well, then this one has to be 1 or psi, because sigma times sigma is 1 plus psi. But then the next one, well, 1 times psi is psi. Psi times sigma is also, sorry, I said 1 times psi is psi, but I mean 1 times sigma is sigma. But then sigma times psi is there. So this one has to be sigma. There's nothing. And then repeat, this one can be 1 or psi. Sigma, 1 or psi. So it's just an Ising model, but on on L over 2, if you wish, if I do this for all sides. So this is just the Ising Hilbert space. Haven't done the Hamiltonian yet. On half. And of course, in this picture, it's an edge, but we can just think of this as now living on a side. So that's my Hilbert space. No, you can, any object in the category you can define a lattice model for. Now, turns out you can see in okay, so there's a formula here that I didn't write down, but you can check that dA, dB, actually by using this rule here, I should have said this before, is NABC DC. So the point is, if the quantum dimension is 1, well, then there's only one thing that can be on the other side here. And that will make a very boring lattice model, because that just says what goes here. I mean, it may not be the same, but it's determined. So basically, you need an object with a quantum dimension greater than 1. And in fact, it's not hard to show, good exercise, in fact, that the dimension of the Hilbert space is roughly grows at large L. So this is L size, grows as the quantum dimension d to the L. And you can easily check that formula there for Ising. This would grow as square root of 2 to the L, which sounds funny, but that's 2 to the L over 2, and it's a. So anytime you do that. So another example of one that people like to do is here. No, there's no reason whatsoever. Yeah, you can take a superposition, you can take anything. And people have, yeah, it doesn't matter. It doesn't have to be a simple object. But today, it will be simple objects. But that's right. There's lots of interesting models where you don't do that, and many more to do. So for example, there's this famous model called the Fibonacci chain, or sometimes the golden chain, where there's only 2 objects, 1 and tau, and you put taus there. And so then next to a 1, you always have to have a tau, but next to a tau, you can have 1 or tau, and so on. So this dimension of the Hilbert space will grow as the golden mean.
Next one is that 1, 1, 2.
No, it's 1 or tau. Oh, right. So no, the point is now this is this thing you were in the beginning. So if it were 1, it has to be tau. But if it's a tau, I can be 1 or tau. And so you see now what happens in Ising, it doesn't really, it just alternates. But I mentioned this because, yeah. Sorry?
It's not translation invariant.
Yeah, sure. Well, because I put a 1 there. But if I allowed this to be a 1 or tau, which I can, so I took a superposition of boundary conditions, what you might call free boundary conditions. So I allowed this or this. Oh yeah, the dimension grows. It grows like this. Well, I mean, the rules don't change. I mean, it depends on what you mean. It's just like saying you add more and more spins. Yeah, right. Right. Yeah. But this one, yeah, it just grows as this funny non-integer number.
Yeah, you generated 2 sigmas, but you didn't count them differently. Right there, you put tau and 1 comma tau. But if I identify the 2 taus, then I would say it's 1 comma tau only. And I would have a period of 1 comma tau, 1 comma tau, 1 comma tau, 1 comma tau every side.
No, because the point is here. Okay, no, this is all good. So the point is here. Okay, so here I'm required, say I do 1 here. Okay, I'm required to do tau there. But now I can do 1 or tau. Right. No, but now the keeping going, so this is, I think, what David means by not translation error. So this is, remember, each one of these is a basis element of the Hilbert space. Each allowed labeling, right? Each allowed labeling is a basis element for the Hilbert space. Yeah. So right. So the point is if I so this, so one thing I could do is just require what's that? I allow one or tau there. So
If it's 1, that gives you tau.
yeah,
If it's tau, that gives you 1 or tau.
that's right.
And then you consider those as 3 cases when you go to the next.
Yeah, exactly.
Here, if it was 1, you
Yeah,
got sigma. If
right.
it's psi, you got sigma.
This is right. This is boring. Yeah. So this is boring. That's why I did this one to show that this reduces to something we know and love, and then and it sounds like I'm going to a great deal of complication to tell you something very,
Try and re-ask the question.
Yeah.
Here it's clear that it's a map to on-site Hilbert space of dimension
Yeah,
2.
right.
Here that's
No, that's right.
there's no such map.
No, that's right.
Are you going to struggle when you try to write down local interactions in
No,
here? You've sort of-
because I'm doing that next. Good. No. Right, because the point is, the key thing is, even though if you look at the entire Hilbert space, you both said, you have to keep going, but I just have to define a Hamiltonian on that Hilbert space, and as long as I define a Hamiltonian that only cares about what's in that region, it's okay. It's perfectly local. Yeah, right. So right, yeah. And as Frank said, if you take periodic, it still is translated. I mean, the rule's the same everywhere, but absolutely, it's a local rule that determines.
The Hilbert space is direct sum of 2 sectors. The Hilbert space in the Ising case here is a direct sum of 2 sectors. You put either.
Yeah, right. So there's subtlety. Let me ask that question again when I get to the topological defect. I will get to that. I may never get to the conserved currents, but that's okay. This is more fun. So yeah, please keep asking questions. Much more fun than. Yeah. Yeah. Yeah, it's just a particular object. It defines the model, and then you can find a model for any row. If rho is quantum dimension 1, it's a stupid model, and you shouldn't look at it. But no, it's a remarkable, beautiful. I should say, people I've seen in talks. I can't claim I'm embarrassed, but they call these Austin Fendley Mung models because we wrote down how to do all this. I mean, but this really goes back to the 80s. Jones and the really cute. I mean, this was known. And then in particular, there was a beautiful paper by the Station Q group in 2006. This paper where they named this model the golden chain. That model had been known before, but they sort of set it all up in this beautiful fashion, and that's where I learned this. Okay, so this defines a Hilbert space. Now we want to define a Hamiltonian. Well, the point is, let's now go back. So hold that in mind. But let's just define an operator, or not an operator yet. Define a picture. I'm going to call it P. I'll call this P chi. And what this is the following. It's just this picture with those labels. So by assumption, we have n rho chi. It's equal to 1. Okay, so that's a picture. Now I'm going to call that p chi, and then I'm going to put a constant in front of here. For reasons you'll see in a second. The reason is because if I take p chi times p chi prime, and what I mean by this is by stack the two, well, then I get a picture that looks like that, right? So that's rho chi. So I stack those together times those constants. So I guess that's constant squared. Oh, sorry, that's chi prime. Well, the bubble thing, which I almost left up, but if you remember the bubble thing I drew at the beginning, so I can now get rid of this bubble. And there's a Kronecker delta between chi and chi prime. So I get that times some numbers, and I chose those numbers there so that that number is 1. Well, I haven't defined that now, but now I'll define an operator. So far, I've just said, I haven't said what they act on, but now, good, perfect segue. I define the operators just to act on this thing here. So I can then put a label here. So P I on the J thing will be the following picture. So Hj minus 1, Hj. So that's the action on this Hilbert space. So each of these pictures, those pictures up there, defines a basis element. And I define this by doing and then I do a bunch of manipulations on this. You get something that's, again, I said I wasn't going to write down the indices, but what you'll get is a couple F's there. You'll see that you sum over Hj, and what you get is an Hj prime. So it doesn't change the 2 ones there, but this one in the middle changes. And you get some numbers there, which you can work out using the rules. So, yeah, you can. That's perfectly fine, as long as you obey the rules. I mean, you'll get the same thing. The point is, whether I do it here or there. Yeah, no, that's the beautiful part about the rules. You can pick whatever definition you want. So yeah, I could have picked the horizontal lines as a basis for these projection. Well, I can call them projection operators or idempotents now. And yeah, that would be a different basis for it, and you would have a transformation. And that's really useful when you're doing a classical model because then you can change lattices around. But no, that's so beautiful about this setup.
Just so I understand, we found one element of the space.
Yep.
Then act between sites j and j plus 1 with this.
Yeah.
And you use this to give you a sum of new elements of the Hilbert space.
Yeah, but the only thing that's changed is that one in the middle, and so that's why it's local. It acts on 3 sites, but it only changes 1, and so it's local. And this defines the operator for every element of the Hilbert space. So now we've got a local Hamiltonian. Well, almost got a local Hamiltonian.
For many of these, it just kind of use the state.
Yeah, okay. I mean, actually, probably generically it doesn't, but certainly it can. Because we've set it up in the Hilbert space. I mean, this diagram will have a non-zero evaluation kind of by definition. So it could be 0, but generically it wouldn't be. Good. Yeah.
Choose the label of next, but you can also choose it to be arbitrary.
Well, yeah. Well, no, that's what I'm going to get. Yeah, okay, good. We keep asking great questions, so I can now segue into the next thing. Right. So the Hamiltonian is then the following. Light. The Hamiltonian. Well, we're going to write it as the sum of H sub j, where j is the site label, and again, I'm going to worry about boundary conditions today. And then each Hj would be the sum over chi, all the chi allowed, and that's finite in by assumption in these categories, times p chi, and then with some coefficient a chi. And that's my Hamiltonian. And at the moment, A is completely arbitrary. I can take whatever I want. Right. No, these do not commute. No, thank you, good. No, these generically do not commute. Even in Ising, they don't commute with each other. So these are not commuting projectors. So if I teach, so good. Thank you for questions. Yeah, I mean, and you can see that in the pictures. Again, sometimes you may find that's true, but actually rarely, it's almost always they don't commute. Yeah, any number at the moment. So the point is, what I'll show you next is that no matter what I choose for the A's, by this definition, and I don't really think I've hidden anything other than technical details, but by this definition, such a lattice model will have topological defects for any A. If you want a Hermitian Hamiltonian. But actually, to be honest, everything I said will work for a non-unitary category. And that's actually with Eric's question, do you need to find a number of objects? Clearly, I can define models where, and I think everything is consistent. People. Yeah. So, right, yeah. So the point is I can define the Hilbert space by gluing these things together. But I'm never going to use that in this talk, but yeah. Oh, sorry. I take that back. No, it's not an orthonormal. It's not an orthonormal. It is a basis. It's a complete basis, but it's not orthonormal. Sorry. Sorry, ask a question again. It's still a Hilbert space, yeah. It's just the way I've written, the basis is not an orthonormal basis. But I think, no, I take it back. That depends on if you choose the correct if you choose the correct boundary conditions, then it's an orthonormal basis. It's an orthogonal basis, and you can fix the normalization. It's an orthogonal basis if you choose the correct boundary, because then basically you glue the two together, and then you see just working down the line. The H's on the top have to be the same as the H's on the bottom. I chose H, by the way, because sometimes these are called heights to make contact with the very old stat mech literature. Yeah, yeah. So generically, you think you glue two pieces together, and it's some graph. But and if the H on the top one and the H on the bottom one are different, they could still be non-zero. But if you're careful with the boundary if you choose the boundary conditions right, then it's an orthogonal basis. It won't be normalized properly, but it's orthogonal.
So the key constraint.
Yeah.
Diagrams that I've seen used so far, I think we've mostly used semi-simplicity.
Yeah.
And so finiteness you could probably get rid of by locally finiteness. You just want your ends to be one only finitely many times or something like that.
Yeah.
And
Yeah. No, people back in the old days defined models that violate all these things, and very few people have gone back and looked. Okay, now we know we get these topological defects. Does that all go through? And the answer is probably, because we're using very little. As far as I'm not going to get to the conserved currents, which is fine. But in that case, then certain simple, you can get these conserved currents very clearly with these simplifying assumptions. In the more general case, it's less clear what you can do. Yeah, I don't know. Yeah, I live in this. Let's just do the case, and the point is you can reproduce basically all of the critical stat mech that people did in the 80s all comes from this, with a few exceptions of people a little bit beyond this. But yeah, and then nobody's visited those questions, so at least as far as I know in this context.
Certainly all
say with the split in half. So different representations can actually embed can be funny space.
Okay, love to have this well, yeah, just since I'm under the gun. You know, if it's relevant to what I'm talking, these are exactly the kinds of discussion I want to have. And in fact, just to jump at the part of the talk I'm not going to do, these conserved currents. So people like Frank and others have looked at these models a lot going back to the 80s. This conserved current business that I had wanted to tell you about, but I'm not going to get to. That's a structure that seems related to the category and all that. And as far as I know, save me, nobody has looked at, you know, when it works. And that has this interesting thing to do with integral. I should have time to at least maybe give a 5-minute preview of that story at the end. Yeah. So good.
If it's big, P of chi, how generic is that type of Hamiltonian? I mean, it's obviously.
No, so right. So you can get basically almost all the integrable trigonometric Hamiltonians from this. You can get, I'm pretty confident, for any rational conformal field theory, I can find a lattice model of this type. So they're certainly not generic in the space of all Hamiltonians you might want to write down, but they're pretty, I believe they're very much a set of a measure non-zero if you start to look at, you know, these certain things. So, and for example, icing, 3-state pots, all these things, the XXZ spin chain, all these can be written in this form. What's special about what?
So you started with this planar three-connected graph. One could imagine building this with fourfold.
Yeah, you could, and you could, yeah. Nothing is special about the threefold. The category would allow you to do all, make sense of all this. Yeah, possibly. I guess if you just did fourfold, the point is by the manipulations you can reduce it to, basically you define the fourfold as sum of threefold. Yeah. Yeah, so I think that's, but what it does do, and what like the integrability literature back then, you know, they would always fix the square lattice for very good technical reasons. They're not always limited to that, but for very good technical reasons, they typically stuck with the square lattice. But this, it makes no difference drawing anyone you want. Yeah. No, well, yeah, but then, well, no, sorry. I mean, yeah, sorry, you can, but then I start to get more confused. Right. Yeah, you'll probably need, yeah. Right, so then you need braiding because you have to bring lines through other lines. Yeah, that's right. And so there are papers, like I wrote one with actually, yeah, she's going to give a talk, I think, at one of the conferences associated with this program. She'll talk about that, I would guess. I should say my former student. Anyway, right. So let me tell you about the topological defects. So I said at the beginning, defining a model this way gives topological defects. So these things that commute with this Hamiltonian, I just wrote down and erased, but I wanted to leave that up there. And the point being, okay, so here I do something that, and let's do periodic boundary conditions just to make life easier. So then this would be H1 again at the end. And then those are the elements of my Hilbert space. And then I draw a ring of 5. So now I evaluate this graph. Well, I can get rid of the loop. And so if we evaluate this, let's turn it into a number as much as you can. I get that, and I get just d phi. So a closed loop just gets you d phi. Doesn't look very interesting. Okay. But now let's remember that, but let's do something different. Let's use this rule. And remember, I wrote this rule where I had 2 lines, A, B, and I had some sum chi, and this was the sum over chi with some, let's not use chi here, let's use, let's use phi, because that's what we're going to do. Let's use H here. So that'll be phi. Call this again. H, right? And there's some D's here. All right. So that's the one where I brought it together instead of making it more complicated. So instead of just getting rid of it now, well, what I can do here is I can glue this thing to that. In fact, let me call this one H prime. Really. Right, so I've got H2 here, I've got H2 there, and then this will be some H prime. Okay, but now I can keep going and drag this all the way through. I do this here as well. And do this. And you see here, then I can notice I've got a thing in here that looks like this, which I can then get rid of, some sum over things, and so forth. And so forth and so on. So the point is, I can, instead of doing the simple thing is just get rid of this loop, I can do this. And I get an action on the Hilbert space. So map. Action on the Hilbert space. So I'm not evaluating, so before evaluating, I'm not evaluating. Just by gluing it in. So that seems stupid. But now you ask, well, I take one of these projection operators and I put it there and do that and do those manipulations I used a few minutes ago to get the value of that. Well, pretty obviously, it doesn't matter which order I do these evaluations in. Maybe I'm a little sloppy, but I think to be clear. So I can either first add the loop, the phi loop, then act with p chi j, any p chi, any chi, any j. Or vice versa. Yeah, after I evaluate, that's right. Yeah. But the point is, it doesn't matter which order I do these things in. Yeah. Well, but the P's not, though. But if I do with the P, yeah, yeah, right. But the point is, it doesn't matter which order I do it in. So, they commute. So H commutes with the thing. So I'll call that d phi. That's d phi is the act of adding this phi and acting on the Hilbert space. And so that's a topological defect. So I have a topological defect. Yeah, any object. So if the quantum dimension is 1, well, it's the identity, this is trivial, but if the quantum dimension is 1, it's an ordinary symmetry. It generates an ordinary symmetry. If the quantum dimension isn't 1, it generates what's typically a non-invertible symmetry. Yeah. It can be either. Yeah. No, in fact, you look for, even in the simplest cases, you'll get both, like icing.
So if the quantum dimensions are not trivial, you are guaranteed that there's some anomaly, so it cannot be uniquely gap grounded.
Right. Right.
So it has to be symmetry breaking or gapless.
Well, yeah. This doesn't specify that. So you have now that's additional information. Yeah. In some cases, yeah. I mean, so not in general. It's just a model, but the key thing we've added by writing the model in this way is we now know there's this topological defect. There's this non-invertible symmetry that may or may not be obvious. So it gives you a useful added piece of information, but generically, no, it won't be integrable. Exactly, exactly. Yeah. So so icing, for example, maybe I'll conclude with just saying how this works for icing. Yeah. So basically, if you take the A's to be uniform in space, in icing, there's really only one non-trivial A you can pick, but you make it uniform in space, and then it's critical. And if you make it non-uniform in space, it's like staggered. That's how you get the off-critical. Yeah, so the thing they call the golden chain is, again, uniform in space. There's only, if you demand uniformity in space, it's a unique Hamiltonian in that case. No, it's the tricritical, well, it depends on the sign in the Hamiltonian. It's either the tricritical icing model field theory or so this was discussed in a very old paper I wrote with Sabir Sachdev and Krishnendra Singh Gupta before the golden chain paper. The work goes back to Baxter and the Hamiltonian version's written there.
You could actually act nearest.
Yeah. So
it's not anymore
right.
critical. No? There's no guarantee anymore.
No, that's right. So, well, it's irrelevant, so it'll stay critical for a bit. But right, so I can now, there's nothing stopping me. Yeah, good. So it commutes with each p chi individually. So sorry, I should say the d phi commutes with p chi individually. So of course I can do products of p. Yeah, I can make longer range interactions by taking products of these projection operators, and then change the physics. So this doesn't fix any of that. So this is just saying in these models, well, at least in the models that we had written down before but not known this, there's a symmetry. So the golden chain being an example of that. So the model was known before the Station Q group wrote their paper, but this thing, they called it topological symmetry now. We would call it a non-invertible symmetry, but was completely unknown. And so that's what this buys you. And it's useful information, but of course, one more symmetry doesn't typically solve the theory. And the talk I didn't get to give, the point is this provides well, let me give I'll give the conclusion since I'm running out of time, and then I will give I'll explain, I'll give a little bit more detail on this in the icing ball. So the conclusion and the segue to the talk I didn't get to give was that if you so now if you want to demand something like integrability, the category then sets up this data. And there's a thing called that Vaughan Jones coined circa 1990, a thing called Baxterization. How do you start with the category and define a model exactly like I did? So none of this would have been a surprise to Vaughan in 1990. But then what you can do, there's an additional condition you can demand of these A's. So you have a condition of the A's, and there's some nice equation you can write down, and then that implies integrability. So that's the story there. And then you, of course, have much more information. But that generically, that just isn't true. You write down arbitrary A's, and you'll get gapped and gapless phases. But it highly constrains what's going on, like what CFT you'll get, for example. If it's a CFT, you get. Yeah, well, that was really the topic of the talk. So the point is, the topic of the talk I wanted to give before getting cut off was that within this setup, you can define conserved currents. This was the paper I wrote by myself. You can define an equation for conserved currents that sometimes goes under the name of discrete holomorphicity, but it's a conserved current relation. And if you can find a solution for that, the model typically, and I believe always, is then integrable. But it's it's a linear equation for the Boltzmann weights as opposed to trilinear for Yang-Baxter.
I propose we just gather here again at 2.
Okay. Well, okay. Yeah, no, that was an advertisement if anybody wants to hear me at 2 o'clock. But let me just say a little bit about what happens here for icing, since I did that as an example. And so you see the setup beautifully explains how duality works. So they're icing, let's just do it by erasure. So here's the setup for icing, right? So now let me put a defect in here. It's the sigma defect. So if I put the psi defect, by the way, that implements spin flip symmetry. You can easily see when you work out what's going on. If I had time, I would show you that. So the point is, again, you do this gluing here. So if I did the psi, actually, I could do it. If I did the psi defect, then it would, if that were a psi, it would flip that to 1. So if this were a psi defect. Okay, but sorry, I shouldn't do things by erasure. But then, the point is, if I do a sigma defect, that makes that a sigma. So that's boring. There's some coefficient in there. There's all those D's and all that. Okay, but then if I do this here, I can get 1 or psi. And so it's flipping. With the edges that have a sigma become a 1 or a psi, and the edges that have a 1 or a psi become a sigma. So this is what people call the Kramers-Wanier duality defect. And by what I just said, it commutes with the Hamiltonian. But notice it's doing something funny. It's mapping a model on the original sublattice to the other sublattice. And so that's why the seemingly bizarre thing I did with icing by writing it this actually turns out to be a beautiful way to understand how the duality defect works, because it shifts the thing. Yeah. So this works for the off-critical case, and in the icing example, that would mean taking sort of the diagonal couplings different, so it would be staggered in this leg. You stagger in the AJs. So what Seiberg and Chow pointed out is if you take what we did, Dave and Roger and I actually predated us for icing, and so then if you first of all assume you're at the critical point, so make this uniform. Second, take periodic boundary conditions. What I said again works for any boundary condition. You take periodic boundary conditions, then you do this half integer. You relabel the things, then you can think of it as a symmetry. But that's a very artificial thing to do. But if you want it to be a symmetry, yeah, right. So the way I like to think of it, it's the Hilbert space then is a sum of the two Hilbert spaces, one with the spins on, say, half integer sites and the other on integer sites. So I guess, 10:59, we got 1 minute. So we're making them wait till 11. Any other questions? Yeah.
And also, because the operators you build with the pi are commuting with the symmetry by construction.
Yeah.
The operators you build with the projectors, the pi,
Yeah.
put them on top.
Yeah, but absolutely by construction.
But how do you construct the operators which do not commute, like they are easy and even have x and how is z, no?
Yeah. Well, in icing, you would know. I mean, I've just defined a Hilbert space, so you can define operators. Yeah, sorry, but it was pretty rude of you guys to put a seminar 1 hour after mine. So really rude to organize to do that, by the way. Anyway, yeah. So right. So I mean, we just have a Hilbert space. You define those operators, but then there's no reason they would necessarily have nice properties. But